Hello and welcome to Rapid C++ Development, combining Embarcadero C++ Builder with Microsoft Visual C++. Your instructor is Rob Swindell, Embarcadero MVP.
Let's continue now with rapid application development using Embarcadero C++ Builder and Microsoft Visual C++. We learned in the last video segment that not all object files are created equal. Just because a file has a .obj file extension does not mean that it is compatible with all tools that consume or utilize .obj files. Visual C++ uses and consumes COFF format object files, while C++ Builder tools use OMF format object files. Library files, or .lib files, are collections of object files, so the rules apply to them equally. What we need to do is, rather than statically linking an object file or a library, we need to utilize a dynamic link library, or DLL. That's what this video segment is going to demonstrate. So we're going to create a DLL using Visual Studio. So new project, Visual C++, Win32, Win32 project. And let me see here, I'll put it in the root directory and call it VC test. We need to tell it that it's a DLL and that we want to export symbols. Precompiled header is fine. Okay, so it created an exported variable, an exported function, and then a C++ constructor, in case we need one. And it's a .cpp file, so it's C++. We'll go ahead and build this. Succeeded. So if we look at our output files, so kind of have our mixed source now. We have the original C project, now C++ project, solution file, header file. So it created this vctest.h, which has the function prototype for the function we can call, as well as a global variable, and did the special decal spec for the DLL export magic. And then in the debug directory, that's your output directory. By default, for debug builds, we have our DLL, and we have an import library. Now this import library is going to be in COFF format, which we can't use with C++ Builder, as I previously demonstrated. So we'll need to convert that to OMF format using the COFF to OMF utility, debug vctest.lib, and then we say vctest OMF.lib. Okay, so I'm going to add the import library that we converted to OMF. I want a library file. There we go. vctest OMF.lib. Okay. So now we're going to try relinking this thing. So it's telling us we have an unresolved symbol. When it linked, it didn't find this function. So I'm going to use tlib to look at this library and see if I can see what the issue is. So I want to do tlib/l. Oh, everything is name mangled. So that's why it's not working. It's building as a C++ module, which we knew, and in C++, you need to be able to encode classes and object hierarchy, not just symbol names. So that's why you end up with all this extra noise around function names. So the solution there is back in our Visual Studio project, actually in the header file for this. Actually, what we want to do is export it as a C symbol. Yeah, extern C, like that. And that will disable the name mangling. Now, if you're going to use this in another C project, then you'd want to wrap this if def underscore C++. So we'll build it again. We will create the library again using implib. We'll look at it with tlib/l. Oh, there we go. Now we have a regular looking function name. There's none of this special garbage around it that C++ would put on there. Now, if you're going to have a group of functions that you want to declare in this manner, this extern C, you can use a curly brace and then have an end curly brace. And of course, if you are going to build this for non-C++, so just regular C, you would want to wrap it like that. And that'll also work. So now you can have multiple function or symbols, variables, whatever, defined here, and they won't be name mangled. Let's try building. And it was successful this time. There you go. Now if we run the application, it can't find our DLL. So that's fine. Maybe we can change the debug startup directory so it can find the DLL. Debugger working directory. So I'm just going to force this to the vctest debug directory so that the DLL is in the current directory when it runs, and it should be able to find it then. Voila! And look, it has the number 42. So it successfully called into that Visual C++ demonstration DLL, called that function, got the value back with 42, assigned it to this label's caption. This is probably the most basic example, but we have a Visual Studio generated DLL in C++. We exported some symbols as straight C symbols, so a function and a variable, which we're not actually using the variable here. And then we called that exported C function in the form show handler for this default form. I'll go back to that code so we can see it here in unit1.cpp. Now in a real project, you would rename these units to be more meaningful. And I actually haven't even saved this project yet, so I can kind of do this renaming before I save things and give them better names. But anyhow, in this main form, this is probably what I would call this object, this unit. So this class would become tMainForm. The file name would be mainform.cpp. Anyhow, it's going to call that function, assign the result via ANSI string conversion. So this will take that numeric return value and turn it into a string with ASCII or Unicode characters, whatever is appropriate, and place it into this caption property of the label so that the user can see it. While implib is the preferred utility for creating an import library from a Microsoft Visual C++ DLL, you also have the option of using the Embarcadero COF to OMF utility to convert an import library that was created by Visual C++ and converting that to a Embarcadero compatible OMF import library. So the usage of this tool here, COF to OMF, your options, your input file, and then your output file. In this case, the input file is going to be a import library that was created by Visual Studio, Visual C++. That's a .lib file. And the output file is going to be your OMF import library file name, also ending in .lib. In this case, I'm using this vctest_omf.lib. Now, if I just run this as is without any options, it's quite quiet. We can add the /v option to kind of output the symbols, the names, the function names. We see the function names in our that variable name. And it seems to be stripping off the _f and the _n. So that looks a little bit suspect, but let's try relinking this and running it and see what happens. Actually, it fails to link. And that's not too surprising because we saw that mismatch in the names there. So again, if we look at the options here, we have these -lib : 2-character options, and they have to, first one has to do with C++ name mangling. We're not really concerned about C++ symbols here. Normalizing names instead of aliasing them for standard calls. So this don't perform MSCDecl aliasing. So default is to alias. So we disable that aliasing. So that's that option there. Now it says the imported name is blank, but the internal name is, I guess, the same or unmodified. Now if we relink, link's fine, and it runs fine. So you do have the option of going from a Microsoft created import library to a Borland Embarcadero compatible import library using the COF to OMF utility. The implib utility goes directly from DLL to OMF compatible import library, so it kind of skips a step or skips a file, an intermediary file. Both options are valid and work. There are some different command line options available with the different tools that might be helpful. In this segment, I'd like to dive deeper into the function calling conventions and the compatibility issues that may arise between Microsoft Visual C++ and Embarcadero C++ Builder. On the screen here, I have a comparison between the two primary calling conventions that we'll be discussing. This is documentation from Microsoft. So we have the CDecl calling convention. This is the default calling convention used by Visual C++. It also happens to be the default convention used by C++ Builder, although that's configurable in both tool chains, what the default calling convention actually is. And then there's also a keyword that can be used to decorate function prototypes to override the default. So for the case of CDecl, it's __CDecl, and then for standard call, we also have the __ standard call keyword that we can use, or you can, like I said, use a project setting or even command line options to override this on a file-by-file basis or a complete project globally. If we read the Microsoft description here, CDecl is the default, that's important. It can do variable argument functions, okay, good to know. Creates larger executables than standard call and explains why. And then over here on standard call, so when calling Win32 API functions, standard call is used. So these are the Microsoft APIs provided with the operating system. That's kind of not important to us since we're not generating Microsoft Win32 DLLs. It's not that critical. But in our case, we don't know. The DLL that you may be dealing with may have been created using standard call, so we'll need to determine that. And explains that variable argument functions are not supported when using standard call. So if you have any function with variable arguments, then you must use CDecl. And going down into the detail differences here, this kind of helps explain things. So we have the argument passing order is the same. It's right to left. We have a little bit difference in the stack maintenance responsibility, whether the caller or the callee cleans up the stack. And then we have a bit of a difference in the name decoration. So these are the exported symbol names, functions, and variables that are exported, and how they are modified or decorated in the actual DLL or import library created by the tool. So even though Microsoft here says that the underscore prefix is used for CDecl functions, except when CDecl functions that you see C-linkage are exported. It has that exception there. If we look further under decorated names, it kind of goes into more detail. And here it says the calling convention CDecl, there's always a leading underscore. So there's no exception here about when C-linkage is used. And since we are providing a C API, we are using extern C-linkage. Also important to note, when you're dealing with 64-bit, your executables and libraries, functions are not decorated, so it doesn't apply in that case. But since we're focusing on 32-bit in this video series, we do have these issues that we need to deal with. Under standard call, you have the underscore prefix, and then you also have an @ and then a number, which is like a suffix after the name. And that indicates the number of bytes that are pushed on the stack and need to be cleaned up following the function call. So they do look a little bit different. The big giveaway is this @ number portion here. If we see that, then we know it's standard call. So if you're given a DLL that you need to investigate, in this case I used the Microsoft tool dumpbin /exports and running it on a DLL, and it'll tell me the name of the symbols that have been exported. And in this case, we have this underscore hello world. It's actually a little bit more useful to look at the import library that's generated by Visual C++, and that gives you the name more clearly, underscore hello world here. We have no @ sign, we have no number following the symbol name, so we know this is using cDecl. Of course, we have the source code. We can verify in the source code of the project that it did not include a decoration here, that cDecl or center call keyword. In this case, the DLL macro is being defined to nothing, so there's no additional code here. But we don't know, just by looking at the DLL or the source code, what compiler options were used. So it's possible that if it was built using command line tools, that the default calling convention could have been overridden. Or in the project file, if it's using a Visual Studio project file. I'll show you where to find that setting here. It's under C++ compiler, advanced options, calling convention, and it shows you the command line option you can use to override that. But the default here is cDecl, and you have options to override that. So in C++ Builder, you also have a project setting to globally set the calling convention. That is under here under C++ compiler, general compilation calling convention. The default is C, which corresponds to that cDecl calling convention that we've chosen. The default here is cDecl, and you have options to override that. So for this experiment, let's go ahead and do that. We're going to rebuild this DLL, and then we'll look at it again using one of these tools. So it also rebuilt the import library, this .lib file. So now when we look at it, the symbol has the suffix, the @ and then the 0. The 0 corresponds to this void here parameter passing specification saying that there's no arguments to this function, so 0 bytes on the stack need to be cleaned up. If we change this function, say, to accept an integer, let's do this as an experiment. Rebuild and then look at it. I would expect a 32-bit integer, 4 bytes. That should be @4 now. There we go. So now we've changed our function name to hello world @4. So I'm going to go ahead and go back to the default. Here, cDecl, rebuild this. Confirm. Okay, our symbols. And you can use the Embarcadero tools as well, like tdump, for example. This will confirm that the symbol name here is underscore hello world without the suffix. That's using tdump-c for a COFF file because we're looking at the Microsoft generated import library, this .lib file here. Now, in using this file in our project, I've created a simple C++ Builder application that's just going to call this hello world function. So it's including the header file for the DLL, which defines that function. And it's going to call that function and assign the value to an edit control here. So that's all that line does. Edit one text equals hello world. Now, as before, you need to have the import library in your project. If you don't have the import library in your project and you attempt to build and run, it's going to fail to link because it can't find that symbol hello world. No matching function for call to hello world. So we're going to add that import library. Oh, I'm missing a step. I cannot add the Visual C generated import library. I have to convert that using implib. This is the Embarcadero tool to generate a OMF import library, which is compatible with C++ Builder. And the input is the DLL file. So we're going to say implib and then uctest omf.lib, debug, and then the name of the DLL. Now we can add that file to our project. a build should succeed if the names match. So here's where we're going to identify an issue. It's looking for hello world, yet our symbol is, we've already covered, the symbol is actually underscore hello world. So to do that correctly, when we call implib on that DLL, we actually need to pass an argument to control the output a little bit more. So that's this -a, which adds the underscore alias for MS Flavor cdecl functions. So we need to add that argument, -a, and then we'll run that. Ta-da! So something I want to stress is that if the calling convention does not match, if you actually have that mixture of cdecl and standard call, more specifically, if Borland tool thinks that the calling convention in the DLL is standard call, but it's actually cdecl, it'll seem to work. It'll actually work probably 99% of the time. You'll end up with a little bit of stack corruption. A recent quote I read that I liked is that memory corruptions are like ricocheting bullets, and that you don't know what they're going to hit or when they're going to hit or how much damage they're going to cause, but much of the time they don't cause any damage. An anecdotal story, I had a project that's a mixed project like this using Visual C++ and CBuilder. And for about 20 years, it actually had mismatch calling convention between what Visual C++ was generating and what C++ Builder was expecting. And it worked. The code all worked. Occasionally, we'd add a function to like a control handler, like a button click event, and we'd get some weird behavior. Get a null pointer, dereference, or invalid instruction, or something like that. It was kind of shrugged off like, well, that's weird, and then we'd put a deferred call in a timer, in a VCL timer on tick handler for that same operation, and it would seemingly work fine. So it just didn't work in that particular event handler. Didn't know why. It comes down to not having the perfect agreement between the calling convention of the DLL and the application that's using the DLL. So it's very important that these match. Just because your application linked and ran does not mean that you necessarily got it right. So you need to make sure, double check that. Perhaps using some kind of profiling tool or runtime validation would catch that kind of corruption as well. But in this is historic example, the code actually ran just fine for many, many, many years. It was only occasionally we had to work around that issue, and the workarounds always seemed to work. So didn't really know the solution until recently.